the brainstem. And the brainstem is going to be subdivided into three components: the midbrain, pons, and the medulla oblongata. Okay, so we can talk about each of these particular components in sequence. Here's a good sagittal view of the brain. What you see here is the left hemisphere. And deep to the left hemisphere is a band of white matter. This band of white matter is called the corpus callosum. Corpus callosum. And the purpose of the corpus callosum is to let each hemisphere know what the other hemisphere is doing. So it carries tracks, bundles of axons from one hemisphere to the corresponding gyrus in the opposite hemisphere. Now, deep to the hemispheres, this little area that's color-coded red is the thalamus. So the thalamus sits along the medialmost aspect of the hemisphere, and so there'd be a thalamus on the other side as well. Sandwiched between the left and right thalamus is a slit-like third ventricle. A ventricle is a cavity or a chamber that houses CSF, cerebral spinal fluid. So, because the third ventricle is slit-like and it's sandwiched between the two ventricles, it's hard to demonstrate it really well in photographs. But the third ventricle is going to sit right between this thalamus and the opposite one, and then fluid from the third ventricle can pass through this little channel here called the cerebral aqueduct into the fourth ventricle, which is situated between the cerebellum and the brainstem. So fluid in the third ventricle can pass through the cerebral aqueduct into this fourth ventricle located between the cerebellum and brainstem. We'll talk a lot more about the thalamus in just a little bit. Now, this area just inferior to the thalamus, we'll call that the hypothalamus. Hypo means under. So together, the thalamus and the hypothalamus contribute to the diencephalon. Now, what you should notice is that hanging from the hypothalamus is the pituitary gland. The pituitary gland hangs from the hypothalamus by a pituitary stalk. Or another name for the pituitary stalk is the infundibulum. Now, even though the pituitary hangs from the hypothalamus, it's not part of the diencephalon.
Hi, Sarah.
All right. The third component is the cerebellum. The cerebellum rides piggyback on the brainstem. It also sits beneath the occipital lobe of the brain, this posterior-most part of the brain here. So it sits behind the hemisphere and rides piggyback on the brainstem. Situated between the cerebellum and brainstem, right in this area here, is going to be the fourth ventricle. And then finally, the fourth component here is the brainstem, and that's going to serve to connect the brain to the spinal cord. The proximal most part of the brainstem, the part that connects with the diencephalon and the hemispheres, is the midbrain. Moving down below, or inferior to that here, is the pons, which means bridge, by the way. Hence the adjective pontine. And then inferior to the pons is the medulla oblongata. The medulla oblongata, once it passes through the foramen magnum, it becomes the spinal cord. That's kind of the layout of the brain. Okay, now, within the brain are four cavities, or spaces, called ventricles, that are filled with cerebral spinal fluid. Now, there are other channels within the brain that house CSF as well. For instance, I mentioned that there was a structure, a channel called the cerebral aqueduct that connects the third and the fourth ventricle. Well, that would be filled with CSF as well. And then there's a long channel that extends down into the spinal cord, within the spinal cord, that's filled with CSF, and that's called the central canal. Now, these ventricles, you already know, are lined by ependymal cells that possess cilia along their apical surface. And the purpose of the cilia is to circulate that fluid. Okay? So it can flow from one ventricle into another and then down the central canal. The composition of the CSF is very, very similar to the composition of plasma. It has to possess the optimal concentration of nutrients and electrolytes to assure optimal neuronal function. Okay? Now, suspended within the ventricles are a network of capillaries called the choroid plexuses. These are specialized capillaries that are also lined by ependymal cells. And the purpose of the choroid plexuses is to secrete CSF into the ventricles. So that CSF is derived from the plasma that's circulating through the choroid plexuses. It says here that the CSF provides for mechanical protection, chemical protection, and circulation. When we talk about circulation, that's a function of the ependymal cells. Chemical protection really refers to the fact that it has to contain the optimal concentration of ions and organic molecules to provide for optimal CNS function. It also provides for mechanical protection. Let's look at the ventricles here. Within each hemisphere, there are two C-shaped ventricles. These are called lateral ventricles. These represent the first and the second ventricles. Notice here there's an anterior horn, a posterior horn, and here's a temporal or lateral horn here. So these lateral ventricles extend into most of the hemisphere. And this red structure here is a choroid plexus suspended within it. Remember, these are the structures that create CSF. CSF is derived from the plasma traveling within the blood of the choroid plexus. Okay. From the lateral ventricles, the CSF can travel through a little opening connecting the lateral ventricles to this slit-like third ventricle. This opening would be called an interventricular foramen.
Shocker.
So it allows movement of fluid from the lateral ventricles into the third ventricle. And then from the third ventricle, it can pass down the cerebral aqueduct to the fourth ventricle, again located between the cerebellum and the brainstem. Now, for the fourth ventricle, the CSF has some options. It can either pass down inferiorly into the central canal of the spinal cord, like this, or it can leave the fourth ventricle through little openings or foramina, of which there are three. Okay? There are these two lateral foramina called foramina of Luschka that allow CSF to escape and flow into the subarachnoid space. The subarachnoid space is a space that surrounds the brain, the spinal cord. And in a very light fashion, it can pass through a more centrally located opening called the median aperture or foramen magendi, where it passes into this larger space called the cisterna magna, and then into the subarachnoid space. So the idea is that there is CSF both on the inside of the brain and spinal cord, but also circulating around the outside of the brain and spinal cord. And along the outside, it's contained within the subarachnoid space. By the way, the term subarachnoid space comes from the arachnoid mata. It's one of those membranes or meninges that surrounds the brain. It's a covering. It's the middle of three coverings. And so the subarachnoid space is the space that's deep to that arachnoid mata. So what we have is a situation where the brain is actually floating or suspended within CSF. Okay? It's suspended within the cranial cavity. Okay? And in this way, the CSF provides for mechanical protection. Every once in a while I'm walking, I might trip.
Oh.
Jeez. Okay? The reason my brain doesn't hit the inner table of the skull is that the brain is surrounded by fluid, which acts as a shock absorber. Okay? That's the mechanical protection we're talking about. Yes?
You said, from the fourth ventricle, the CSF will travel to the spinal cord for all the three parameters.
Right, it can, in other words, it can pass down into the central canal or it can leave the fourth ventricle and travel into the space around the brain through one of those three openings.
But then wouldn't it still go through? Because in the diagram it looks like it still goes through the central canal.
Oh, some of it does go through the central canal.
Well, no, but like if it went to the cranial
There's
cavity.
two foramen lucidum
The
and one
central canal is
foramen.
located within the spinal cord.
Yeah, I think that's
So,
other two.
so if it travels within the spinal cord, it's not going to travel on the outside. So it can either travel within the spinal cord in the central canal, or it can leave the space inside the CSF and travel to the outside.
Okay, I got you.
So it's two foramen lucidum, that's the second hole?
Yeah,
You say
and
that-
there's one foramen of Magendie, which is the third hole.
Is the cisterna magna a part of the arachnoid mata?
It's just an expanded area of subarachnoid space
Okay.
near the base of the brain. Okay. Now, later, along the mid-sagittal area of the brain up here, okay, there's a sinus, which is a dilated vascular channel containing blood. We'll see that the CSF is going to drain into the superior sagittal sinus later. Okay. If right now we've talked about the way CSF flows, and we've mentioned the fact that it's produced by these structures called choroid plexuses that are suspended within the ventricles. Now, let's talk about the architecture of the brain. The cerebral hemispheres and the cerebellum have a certain architecture, such that you have what's called gray matter on the outside, and the outer region is called the cortex, and white matter that's deep to it. So this outer cortical region in here is made up of gray matter, and deep to that we're going to see white matter. Read that on the slide here. You can see how the cerebral cortex here is made up of gray matter, and deep to it is this white matter. And it's called white matter because it contains myelinated axons that impart that color. Whereas the gray matter consists mostly of nerve cell bodies. And remember that nerve cell bodies do not have myelination. Even if a neuron is myelinated, it's only the axon that undergoes myelination. In a very like fashion, if we look at the cerebellum has gray matter on the outside and white matter deep to it. So it has a similar pattern. Let's see if I can find it. Cerebellum. Okay, here's the cerebellum. You see how the white matter is on the inside. In fact, the white matter on the inside of the cerebellum takes the form of a branching tree. And so we call this region of white matter the arbor vitae, which means what? What does arbor mean?
I would say tree of life.
Tree, so tree of life. AE is possessive in Latin. So the tree of life. Okay, so again, just like the hemispheres, the white matter is deep, the gray matter is on the outside, the cortex. Now, what about the diencephalon and brainstem? The architecture is a little bit different. I'm going to give you kind of a section of the brainstem here to demonstrate. Within the brainstem, you have clusters of nerve cell bodies that make up what we call nuclei. And these nuclei appear gray. And you might have multiple nuclei in any section of the brainstem or cerebellum. And then dispersed between these nuclei, you might have bands of myelinated axons, white matter. Okay? So, on first glance, the pattern of gray matter and white matter within the brainstem and diencephalon appears more haphazard, in that you have gray matter interspersed with white matter, as opposed to it being limited to the cortex, gray matter being limited to the cortex, and the white matter being limited to the deeper matter of the brain. Now finally, in the spinal cord, we have a situation that's opposite the brainstem and cerebellum, and that the gray matter is located on the inside. Okay? And it takes the shape of an H, like this, or a butterfly. Whereas everything outside of that butterfly is white matter. And I've taken the liberty to draw the central canal right in the middle of here. That contains CSF. Okay, so I want to say something really important now.